This is a part 2 of structure equation modeling video, and here we will discuss, let's before discussing the structure equation modeling, we have to discuss its overview. So there is the factor exogenous and endogenous. Exogenous, so the first is a relationship between a construct and a measurement variable. If we talk about the exogenous, here is a x, but this is the endogenous, and this is the multiples exogenous variables. We call it relationship between a construct and multiple measurement variable. Here is the C type of dependence relationship between two construct, a structure equation modeling. Here is the construct 1 depend into the construct 2, and this is the correlational relationship between the construct 1 and construct 2. There is a correlation between A and B. The A construct is establishing relation into the 2, and 2 is establishing relation into the 1. So these has these have relationship, correlational relationship between both construct. Common type of theoretical relationship in structure equation modeling. As we discussed earlier, measurement relationship are one from a dependent relationship between construct two variables. The second form is a dependent relationship between construct. Here the arrows point from the antecedent independent variable to the subsequent effect of outcome dependent variable. This relationship is depicted in the figure 1c. In the later section we discussed issues involved in the specify situation which is the special from a dependent relationship. Specification of dependent relationship also determine whether a construct is considered exogenous or endogenous. Recall that an endogenous construct act like a dependent variable, and any construct with a dependent path arrow pointing to it's a considered endogenous. An exogenous construct has only correlational relationship with other construct and act as an independent variable in structure relationship, that is no dependent path coming into the construct. In many instances, the researcher wishes to specify a simple correlation between exogenous construct. The researcher believes the constructs are correlated but does not assume that one construct is dependent upon another. This relationship is depicted by a two-handed arrow connection as shown in figure 1d. An exogenous construct cannot share this type of relationship with an endogenous construct. Only a dependent relationship can exist between exogenous and endogenous construct. Let's talk about the combining measurement of structure relationship. Here in the figure 2 illustrate, which I will show you. This is the figure 2, that is a structure equation modeling overview. We call it the correlational relationship. Exogenous construct has always the correlation relationship. So as a figure to illustrate a simple structure equation modeling incorporating both the measurement and structure relationship of the two construct with 4 indicator each. In figure 2a, there is a correlational relationship between the two construct indicated by the curve arrow. The indicator 4 of each construct are labeled x1 to x8. Figure 2b depict a dependent relationship between the exogenous and endogenous construct. The two constructs retain their same indicator, but two changes distinguish it from the correlation relationship. First, the indicator of the exogenous construct are denoted by x1 to x4, whereas the endogenous indicator are y1 to y4. The measurement variable themselves did not change or at all. Just here is a structure equation modeling overview. As I had mentioned before, correlational relationship, exogenous construct has always intercorrelation relation. Here is the we have the variable x1, x2, x3, x4, x5, x6, x7, x6. So the researcher divided variable for variable. The first variable is here x1 to x4, and the second is the second part, but these variables are intercorrelated to each other. Here is a dependent relationship. Independent relationship, exogenous construct depend on endogenous construct. It means variable 1 depend on y, x2 depend on y2. So that's how this construct is depending ex a- endogenous construct. So exogenous construct, there is a x1, x2, x3, x4. These are the variable which will make the exogenous, and this will impact here, and that will become the y, y2, y3 and y4. Visual relationship, perception and measurement of structure model relationship as per in a simple structure equation modeling. The designation is the model. Second, the single dependence relationship between the exogenous construct and the endogenous construct is depicted by the straight arrow between the construct that replace the curve arrow. The researcher determined whether the construct are exogenous or endogenous based on the theory being tested. Construct the same indicator, but they can different based on their role in the model. A single structure equation model most likely will contain both independent and correlational relationship. How well does the model fit? Let's talk about it. It is important to remember that in the construct to regression analysis, other independent techniques which seek to explain relationship in a single equation, structure equation modeling statistical goals is to test a set of relationship representing multiple equations. Therefore, fit of predictive variables, accuracy for other techniques, that is R2 for multiple regression classification accuracy, indeterminate analysis or statistical significance in MANOVA are not well suited for structure equation modeling. We call it as a AMOS. AMOS is the software where the researcher can analyze their variable while applying the structure equation modeling. What is the needed is a measurement of the fit to predictive accuracy that reflect the overall model, not only single relationship. The researcher must accept or reject the entire model, determining in an overall model fit it is acceptable before examining any specific relationship. Because the focus is one of the entire model, structure equation model used a series of measurements that depict how well a researcher theory explains the input data. The observed covariance matrix among measurement variable model fit it is determined by the correspondence between the observed covariance matrix and estimated covariance matrix. The result from the purpose model, if the purpose model properly estimated all of the substantive relationship between construct and the measurement model, adequately defined the construct, then it should be possible to estimate a covariance matrix between measurement variable that closely match to observe covariance matrix. Will we discuss the process of estimating a covariance matrix from the proposed model along with the number of measurement of fit in much greater detail in the later section in this chapter. Structure equation modeling and other multivariate techniques. Here we talk about the SEM methods and other multivariate technique. In structure equation modeling is a multivariate technique based on the variables in the both measurement and structure models. In this measurement model, each set of indicator for a construct acts collectively as a variate that define the construct. In the structure model, constructs are related to one another. Correlational and the dependence relationship. Structure equation modeling is most appropriate when the researcher has multiple constructs, each represented by several measurement variables, and these constructs are different based on the whether they are exogenous and endogenous. In this sense, structure equation modeling is similarity to have other multiple independent techniques such as MANOVA and multiple regression analysis. Moreover, the measurement model look similar in from and functions to factor analysis. We will discuss the similarities of structure equation modeling to both independent and dependent technique in the following section. Let's talk about the similarities to dependence technique. An obvious similarities of structure equation modeling is to multiple regression, one of the most widely used independent technique. Relationship for each endogenous construct can be written in a from similar to a regression equation. The endogenous construct is the dependent variable, and the dependent variable are the construct which arrows pointed to the endogenous construct. One principal difference in structure equation modeling is that a construct that acts as an independent variable is one relationship can be the dependent variable in other relationship. Structure equation modeling then allow for all of the relationship equations to be estimated simultaneously. Structure equation modeling can also be used to represent other dependent technique. Variation of the standard structure equation model can be used to represent non-metric categorical variable, and the even a MANOVA models can be examined using the structure equation modeling. It's enable the researcher to take advantage of the structure equation modeling ability to accommodate measurement error, for example, with a ANOMA and MANOVA context. Let's talk about the similarities of the interdependence technique. At first glance, the measurement model associated measured variable with the construct seems identical actor analysis where variable have loading on factor. Despite a general deal of similarity such as the interpretation of the strength or of the relationship of each variable to the construct knowing as a loading in a factor analysis. One difference is critical factor analysis of this type of basically an exploratory analysis technique that researcher for structure among variable by defining the factor in term of set of variable. As a result, every variable has a loading on every factor. Structure equation modeling is the opposite of an exploratory technique. It's required that the researcher specify which variables are associated with each construct, and the loading are estimated only where variable are associated with construct. Typically there are no cross loading. The distinctions in not so much with interpretation as with implementation. Exploratory factor analysis required no specification on the part of the research. In contrast, structure equation modeling required complete specification of the measurement model. The advantage of using multiple measurement for the construct discussed earlier are realized though the measurement model of the structure equation modeling. In this way, the estimation procedure for the structure model can include a direct correlation for measurement error as discussed earlier. By doing so, the relationship between the construct are estimated more accurately. Let's talk about the emergence of structure equation modeling. Structure equation modeling is a relatively new analytical tool, but its root extend back to the first half of the 20th century. Structure equation modeling development originated with the desire of genetic and the economics researcher to be able to estimate causal relationship between the variable. The mathematical complexity of the structure equation modeling limited its application until computers and software become widely available. They enable the two multivariate procedure of the factor analysis and the multiple regression to be combined. During the late 1960s and early 1970s, the work Jorskog and the Serban lead the simultaneously maximum likelihood estimation of the relationship between the construct and the measurement indicator variable as well as among latent construct. This work this work cultivated in the structure equation modeling program LISREL, that is it was the first software to perform structure equation modeling of the path analysis, but it was the first to gain whispered use. Structure equation modeling growth remained relatively slow during the 1970s and the 1980s in large part of the world. Its perceived complexity by 1994, however, more than 150 structure equation modeling articles are published in this audience social science literature. That number of increased to more than 300 by the 2000, and the total structure equation modeling is the dominant multivariate technique followed by the cluster analysis and MANOVA. The role of theory in structure equation modeling. In structure equation modeling should never be attempted without a strong theoretical basis specification of the both the measurement and structure models. The following section addresses some fundamental roles played by the theory in structure equation modeling, specifying relationship that define the model, establishing causation particularly when using the cross-sectional data, and the development of the modeling strategies. Specifying relationship. Although theory can be important in all multivariate procedure, it is a particularly important for the structure equation modeling because it is a consider a confirmatory analysis that is it is useful for testing and potentially confirming theory. Theory is needed to specify relationship in both measurement and structure models, modification to the proposed relationship, and many other aspects of estimation a model. For a practical perspective, theory-based approach to structure equation modeling is necessary because all the relationship must be specified by the researcher before the structure equation model can be estimated. With other multivariate technique, the researcher may have been able to specify a basic model and allow the default values in the structure statistical programs to fill in the remaining estimation issues. This option of the using default value is not possible with the structure equation modeling. In addition, any model modification must be made through the certification by the researcher. Thus, when we stress the need for theoretical justification, we are emphasizing the structure equation modeling is a confirmatory method guideline more by the theory than by the empirical result. The depreciation of the set of relationship in a path of diagram typically involve a combination of dependent and correlational relationship among the exogenous and endogenous construct. The researcher specify any combination of relationship that have theoretical support for the researcher question at hand. The following example illustrate how the relationship can involve both uh, ex, and the correlational element as well as the accommodation interrelated relationship. Figure 3 shows three example of the relationship. Here is a figure 3 which shows the three example of the relationship, the causal relationship part diagram x1 x2 impact on the y1. So here is a x1 x2, these both construct are depending on the variable y1. So figure 3 shows the three examples of the relationship depicted by the path diagram along with the corresponding equations. Figure 3 shown as a simple three construct model, both xy and x2 and exogenous construct related to the endogenous construct y1, and the curve arrows between the x1 and x2 shows that affects the intercorrelation multicollinearity and the prediction. We can shown it a relationship with a single equation much as we did not in our discussion of multiple regression. In figure 3b we added a second endogenous construct y2. Now it is addition to the model and the equation shown in the figure 3a. We add a second equation showing the relationship between x2 and y1 and y2. Here we can see the unique role of played by the structure equation modeling. When more than one relationship share the construct, we want to know the effect of x1 on y1, the effect of x2 on y1, and the simultaneously the effects. The structural equation modeling, here is a causal relationship where the independent variable depend on the dependent variable x1 and x2. These are the independent variable which is depend on the dependent variable. So if we see in the picture, so x1 and x2, these two variable are impacting on the y1, that is a dependent variable. So here is a in this example b, we have the x1 x2, x1 x2 x2 and y1. These are impact on y1 and y2. So here is we have here is two dependent variable and two independent variable. So x1 and x2 both independent variable are impacting on the dependent variable, that is a y1, and here is a x impact on a dependent variable, and y is all also depend on the dependent variable y1. But here is a y2 depend on the x2, but y1 is also impacting on the y2. Here is a multiple variables we have and there is a three dependent variable y1, y2 and y3. Here is in this picture, as it is clearly shown that y, x2 and y3, these has a intercorrelation relationship between the dependent and independent variable. So x1 of x2 and y1 or y2, if we did not estimate them in a consistent manner, we would not be measured of representing their true and separate effect. For example, each of our technique is needed to show the effect of x on the y1 and y2. The relationship become an more intertwined in the figure 3c with the three dependents construct such as related to the other as well as the interdependence construct. As a reciprocal relationship, two-handed straight narrows even occur between the y2 and the y3. This relationship is shown is the equations by y2 appearing a prediction of the y3 and y3 appearing a prediction of y2. It is not possible to express all the relationship heaps of the either figure 3b or 3c in a single equation. Separate equation are required for each dependent construct. The need for a method that can estimate all the questions simultaneously met by the structure equation modeling. These examples are just a preview as to the type of relationship that can be that can be that can be showcased and then implementally examined through the structure equation modeling. Given the ability for the model to become complex quite easily, it is even more important to use theory as a guideline factor to specification of both the measurement and the structure equation modeling. Later in this chapter, we will discuss the criteria by which the researcher can specify structure equation model in the more details. Let's talk about the establishing causation. Perhaps the strongest type of the theoretical interface a researcher can draw is a causal interface, which involves proposing that independent relationship actually is based on the causation. A causal interface involves a hypothesized cause and effect relationship. If we understand the cause sequence between variable, then we can explain how some cause determine a given effect. In practical terms, the effect can be at least partially managed with the some degree of certain, so independent relationship can sometimes be theoretically hypothesized. Cause, however, a simply thinking that independent relationship is casual doesn't make it so. Then, as we use the simple term cause with great care is structure equation modeling. Let's us consider BHAT as interest in job satisfaction as an example. If feeling positive about a supervisor can be proven to result in cause increased job satisfaction, then we knows the higher job satisfaction can be achieved by improving how employees feel about their supervisor. Those company policies and training can focus on improving supervision approaches. If supervision is casually related to hypothesis, then the resulting improvement will increase employees' job satisfaction. Casual research design traditionally involve an experiment with some control ma- manipulation. For example, a categorical independent variable as found in MANOVA or ANOVA. Structure equation modeling are typically used, however, in non experimental situation in which the exogenous constructs are not experimentally controlled variable. This limits the researcher ability to draw causal interface, and structure equation alone cannot establish causality. If can however treat dependence relationship as a causal if core type of the evidence covariation sequence non-superiority covariation and theoretical support are reflected in a structure equation model. Let's talk about the covariation because causality means that a change of the causal bring about the corresponding changes in an effect systematic covariance correlation between the causal and effect of necessary but not sufficient to establish causality, just as it done in the multiple regression by estimating the statistical significance of coefficient of independent variable that affect the dependent variable. Structure equation modeling can determine systematic and statistically significant covariance. We being construct those the statistically significant estimated path in the structure model. That is the relationship between the construct provide the evidence that covariance is a present structure relationship between the construct are typically the path of which causal interface are most hypothesized. Let's talk about the sequence. A second requirement of causation is the temporal sequence of the event. Let us our earlier example as a illustrate. If the improvement is supervision, result is increased job satisfaction, then the change in the supervision cannot occur after the change in job satisfaction. If we picture many domains standing in a row with the first one of the knocked down by the small ball, it may cause all of other domain fall. In other words, the ball hitting the first domain cause the other domain to fall. If a ball is the cause of the effect, the ball must have the first domain before the other fall down. If the others have fallen down before the ball strike the first domain, then the ball cannot have caused them to fall. Those sequence in causation measurement that improvement in supervision must occur before the job satisfaction increase if the relationship between the two variables is causal. Structure equation modeling cannot provide his type of evidence without a researcher design that involve either an experiment of longitude one data an experiment can provide this evidence because the researcher maintain control of the causal variable through manipulation. Those the researcher first manipulate a variable and the observe that effect. Longitudinal data can provide this evidence because they enable us to occur for the time period in which events occur. A great deal of social science researcher on cross-sectional survey measurement all of the variable at the same point in the time does not provide a way of accounting for the time sequence. Those the theory must be used argue that the sequence of effect is formed on the construct to another. Non-superior covariance. A superior relationship is one of the false or misleading. Any relationship is considered superior when another event not included in the analysis actually explain both the cause and effect. Simply put, the size of nature of the relationship between the cause and the relevant effect should not be affected by including other construct a variable in a model. Many antecedents describe what can happen with superior correlation. For example, a significance correlation between the ice cream consumption and the likelihood of the drawing can be empirically verified. However, it is a safe to say that creating the ice cream goes down we if we account for some other potential cause, that is the temperature is associated with increased ice cream consumption and more swimming, we would find not real relationship between the ice cream consumption and the drawing. Those we cannot say with any certain that ice cream consumption cause the likelihood of drawing even though they are significant correlated. The impact of collinearity. Let's talk about its impact on collinearity. Because of the causal interface is supported when we can show some third construct does not affect the relationship between the cause and effect. Lack of the collinearity among the predictor is a desirable. When collinearity is not represent, the researcher comes close to reproducing the conditions that are presented and desirable. When the culinarity is not present to researcher comes closest to producing the condition that are the represent in an experimental design. These condition include orthogonal and uncorrelated experiment prediction variable. Unfortunately, most structure model involve multiple predictors construct that exhibit multicollinearity with both other predictors and the construct in these case making a causal interface is less certain. Therefore, in structure equation models involve cross-section survey approaches. When other predictor constructs are included in the model and when the effects construct error is independent of the causal construct. Testing for superiors relationship. In figure 4 shown an example of the testing for an non-superiors relationship which two structure equation models. The first model specifies the proposed structure relationship between the two constructs. The second model incorporates the alternative cause construct as an additional prediction variable if the estimation relationship between the structure found in the first model remain unchanged with the additional predictor is added to C and model, then the relationship is deemed non-superior. However, if the structure relationship become most non-significant in a second model because of the additional of the other predictor, then the relationship must be considered superior. We should note that more than one additional construct may be added and that the structure relationship must remain significant no matter how many constructs are added. In our employees' job satisfaction example, we propose that supervisor perceptions influence satisfaction. Figure 4a. One could argue, however, that how employees feel about their superior does not really determine their level of satisfaction with their job. An alternative example, for instance, is that good working condition as alternative cause for both improved supervision and higher job satisfaction. Figure 4b first the working condition construct is measurement along with the other construct and the relationship is a specified between working condition and both supervisor and the job satisfaction. The structure equation model can determine whether a relationship between the construct and the exit or not. In other example, the estimation coefficient remain unchanged. Point 50 indicating that the relationship between the supervisor and job satisfaction is non-superior. If the estimation coefficient had become non-significant, then working condition is added to the model, then we would consider the relationship between the supervisor and job satisfaction to be superior. Original relationship supervisor job satisfaction. Point 50. Here is a figure B, that is a testing alternative causality, working condition, supervisor and job satisfaction. Supervision impact on the job satisfaction. Point 50 and working condition is point 30, and there is a point 00 difference between the working condition and supervision. Testing for the non superior relationship between the construct. Theoretical support. The final condition for causality is the theoretical support of the complying relationship of support, a causal and the effect relationship. This condition emphasizes that the simply become especially important than cross-sectional data. A structure equation model can demonstrate relationship between any construct and any other correlation with one another. For example, ice cream consumption and the drawing statistical. But unless theory can be used to establish a causal ordering and the rationale for the observed covariance, the rational relationship remains simple associated and should be the attributed with Any further casual power? Do employees feeling about their supervisor cause job satisfaction? A theoretical justification for a casuation many exist in that as a employees spend more time with their supervisor, they become more familiar with their supervision approaches, which increase their understanding and the reaction to the supervisor, and based on the experiment they become more satisfied with their job situation. Those a case can be made that more favorable feeling about supervisor cause increase the satisfaction. Although structure equation modeling is often offered to as a casual modeling, casual interface are not possible when evidence is consistent with the four conditions for causality already mentioned. Structure equation modeling can provide evidence of the systematic covariance and can be help in demonstrating that relationship is not the superior if the data are longitudinal. Structure equation modeling can also help establishing the sequence of the relationship. However, it is up to the researcher to establish theoretical support. Those just structure equation modeling is helpful in establishing causal interface, but it cannot do it alone. Developing a modeling strategy. One of the most important concepts in a research must learn the gardening multivariates technique is that no single correct way exists to apply them. In some instances, a relationship are strictly specified and the objective is a confirmation of the relationship. At At another time, the relationships are loosely recognized and the objective is the discovery of the relationship. At each extreme, as well as the points in between, the researcher must apply the multivariates technique i- in accordance with the researcher objective. The application of structure equation modeling follows is same talent. Its flexibility provides researcher with a powerful analytical tool appropriate for many research objectives, which serve as a guideline in a modeling strategy. Those used of them strategy is designed to denote a plan of action toward the specified outcome. For our purpose, we define three distinct strategies in the application of structure equation modeling: confirmatory modeling and strategy, competing modeling and strategy, and the mode development strategy. Confirmatory model strategy, which I will talk about the further video. I will call it, that video will be the third video of the structure equation modeling.